Hello everyone, my name is Guerguis. I'm an assistant professor of design and structural technology and McCarthy Hosepel McCarthy Endowed Professor at the College of Architecture and Design, University of Tennessee in Knoxville. I'm also the director of Soft Boundaries Lab. I'm very excited to present our newly developed course on visualizing structures, integrative methodology for teaching structure principle to architecture students. So traditionally, technology courses such as structures are typically taught to architecture students in silos. That is, they tend to be lecture-based, theoretical, and separated from the core architecture design studios. So translation of these abstract structure principles into design concept is usually challenging, resulting in either compromising of the design intent or unrealistic structure solutions. Therefore, there is a necessity for a pedagogical overhaul to address these challenges in academia. To address these challenges, the work presented in this paper proposes a comprehensive four-module active learning approach, which includes first, manual calculation, second, computational structure analysis and form-finding simulations, third, physical models, fabrication, and load testing, and finally, design studio integration. So the course started by introducing the students to the fundamental of mechanics, and then the following exercise was designed to identify the magnitude and the direction of resultant of four forces using vector algebra and grasshopper and rhino. The students then experimented with additional forces scenarios with varying directions and magnitudes to visualize the impact on the point of application, direction, and magnitude of the resultant forces. Next, to introduce the students to the three equations for equilibrium of the beam, the students performed manual calculations first to determine the reaction forces of the beam loads, then followed by computational exercise that replicate the same problem using Caramba. Students can experiment and visualize beam behavior with different materials and load scenarios. This provided the students with first-hand observation of the impact of these parameters on the overall performance of the beam while observing the changes in the shear moment diagrams and bending failure under each scenario. Physical models demonstrate the findings from the previous exercise, allow the students to investigate the performance in relationship to its cross-section. Test results confirm that the wide flange section profiles perform the best since it has the most of material concentrated in the flanges with the greatest possible distance from the neutral axis. This activity introduces the students to the physical load testing procedure in the course. Starting investigating long-span structure system, this exercise explored the analysis of planar truss, constructing and comparing multiple types of truss models. This exercise focused on identifying areas of compression and tension that helps the student evaluate the mass, displacement, and the stress. Students were able to associate the impact of topology and of the members arrangement on the truss strength and performance. For the first lab assignment, the students were asked to design and build bridges to integrate their structure analysis method and design principle explored in the computation like topology optimization. Students were asked to design, analyze, and simulate their own trusses. Then the students used Caramba and Grasshopper to optimize the design using an evolutionary solver. After a design analysis, students fabricated and load tested their bridges with a model that spanned over 1 meter. By conducting these load tests, the students observed firsthand how the forces act on the structure to identify locations of failure as well. The students were introduced later to computation form finding using Kangaroo Physics Engine. The goal was to create a shell mesh that simulate the behavior of a hanging chain model. This workflow, students were able to experiment with different space truss configuration, observing the stability and generated designs and calculated the reactions at the supports. Additional methods of form finding were studied through both digital and physical model simulations. That enabled the students to explore and create lightweight structures, such as tensile structure. This digital approach allowed the students to simulate the tensile forms and compute the forces and the principal stresses within their models. Then a manual approach was followed by let the students build the fabric membrane recreate of the digital model. In the second half of the graduate level course, the focus shifts to more research-driven of contemporary structural research topics. For this one, the students will be able to have an experimentation with 3D printed non-reinforced vernacular Catalan or Gustaviano vaults. So working in tandem with the technology courses, I have developed a series of design studios titled Extraordinary Methods in Architecture, that incorporate the structural principles from the technology courses and was offered at both undergraduate and graduate level. See, the example in this drawing is a long span space frame for a music hall design proposal for the studio. This is another example from a different studio that investigated the design of a non-orthogonal skyscraper. The image on the left shows a series of structural models that help the students understand the hierarchy of the complex structure system within the tower. So to conclude, with a successful newly developed curriculum and the core strategies described in this paper, we illustrated that conceptual understanding of structural systems can be achieved through integrative active learning approaches. The students were able to integrate concepts of high structural complexity developed in the technology courses directly into their design studio projects. Additionally, this paper showed that the new direction for use of computational structure analysis and digital fabrication and form finding to observe the structure assembly's behavior on different material performances. The authors consider this research as the first step towards a novel, fully integrated approach to more comprehensive and curriculum driven by active learning methodologies, and has the potential to transform the current pedagogical practices in preparing the next generation of world-class architects. I would like to thank research assistants Kristen Pitts and Nicholas Van Son for their work in this project, University of Tennessee Office of Teaching and Learning Innovation, and the College of Architecture and Design for their support of developing of this course. I also like to thank Clemens Bresinger and Karamba team for providing student licenses, and the International Association for Shell and Spatial Structures Conference Organizing Committee and the University of Surrey. Thank you for joining me today and looking forward to meet you at the conference.